Bismillahirrahmanirrahim. A theorem which state that if the set consists of all linear transformation from the vector space U to the vector space V over the same period F is a vector space under the condition of addition and scalar multiplication defined by t1 plus t2 x is equal to t1x plus t2x, and alpha t1 x is equal to alpha multiplied by t1x for x is an element of the vector space U, and t1 and t2 are the linear operator from the vector space U to the vector space V. Prove under to check the condition of all the vector spaces over the field F. Under addition, let T1 and T2 be two linear transformation from the vector space U to the vector space V such that therefore T1x, T2x are the element of the vector space V. That is, if x is an element of the vector space U, then Tx1 will be an element of the vector space V. And again, when we apply T2, the linear operator T2 on the same element x of the vector space U, which gives an element of the vector space V for an element x belong to U. Since T1 plus T2 x is equal to T1x plus T2x according to our hypothesis, and T1x and T2x both are the element of the vector space V over the field F. Therefore, the addition of the element of the vector space V over the field F is again an element of the vector space V, and this is equal to T1 plus T2x. Therefore, T1 plus T2 is a function from the vector space U to the vector space V. According to this condition, that is T1 plus T2, when we apply T1 plus T2 on the element x of the vector space U, the result is the result of the T1 plus T2 on x is again an element of the vector space V. Therefore, T1 plus T2 is a function from the vector space U to the vector space V. Now to check that T1 plus T2 is a linear operator from the vector space U to the vector space V. Therefore, for any two element x, y of the vector space U, alpha, beta are any two scalar, then the linear combination alpha x, beta y is again an element of U according to the condition of the vector space. And when we apply T1 plus T2 on this resultant element according to our this condition, which will be equal to T1 alpha x beta y according to this condition, plus T2 when we apply T2 on the single element, this which will be equal to T2x. This resultant element is a single element which is equal to T2 of this element, and T1 and T2 are the linear operator. Therefore, according to the definition of the linear operator, this result is equal to alpha T1x beta T1y, and T2 is also a linear operator. Therefore, this result is also equal to alpha T2x beta T2y, and alpha is common in these two terms, which is equal to alpha T1x T2x, and beta is common in these two terms, which is equal to plus beta T1y plus T2y. Now, x is common. X is an element of the vector space U, which is equal to, according to this condition, T1 plus T2x, and Y is also an element of the vector space U. Therefore, according to this condition, we can rewrite this as beta multiplied by T1 plus T2y. That is, the operator T1 plus T2 also satisfy the condition of the linear operator from the vector space U to the vector space V over the field F. Now to check the second condition, that associative property with respect to addition. Now let us select three linear operator T1, T2, T3 such that T1 plus T2 plus T3 apply on the element x of the vector space U over the field F is equal to, according to this condition, T1 plus T2 x plus T3 x according to this condition, and T1 plus T2 x is equal to T1x T2x plus T3x. Since T1, T2, T3 are the element of the vector space V over the field F, therefore associative property hold in these in the elements of the vector space V. The T1x, T2x, T3x are the element of V. Therefore, associative property is hold in these elements of V. That is T1x, T2x, T3x, or T1x, T2x, T2, T3x according to this condition, or T1, T2, T3 on whole element X. That is associative property hold in the set of linear combination from the vector space U to the vector space V. To check another condition, the existence of an identity linear transformation. That is, we define a zero mapping 0 from the vector space U to the vector space V, defined by 0 when we apply the zero function on any vector of the vector space U, the result will be equal to 0 of the vector space V. For any two element xy of the vector space U and two scalar alpha beta, the alpha x comma beta y is again an element of the vector space U, and when we apply the zero mapping on the element and this resultant element, the result will be equal to 0 according to the given condition. 0 can be written in the form of 0 plus 0. 0 is 0. This is an element of the vector space V, and the 0 is an additive identity element of the vector space V. Therefore, 0 plus 0 is again equal to 0, and this result can also be written in the form of alpha multiplied by 0. 0 is an element of V, and alpha is a scalar, is again equal to 0, and beta is another scalar. Beta multiplied by 0. 0 is an element of the vector space V, is again equal to 0. That is alpha multiplied by 0. This result 0 can also be obtained from the when we apply the zero mapping on the on X, an element of U, and apply the zero mapping on the element y of the vector space U. That is the 0 from the vector space U to V is also a linear operator, and consequently is an element of the set. And for any linear transformation T1 and 0, linear transformation 0, 0 plus T1x is equal to 0 x gamma T1x according to this condition. For x is an element of the vector space U, and 0 multiplied by, when we operate the 0 function on x, the result will be equal to 0 plus T1x. That is 0 plus T1 is equal to T1. That is 0 is an additive identity of this set. To check the next condition, that is additive inverse. For a linear transformation minus t from U to V defined by minus tx is equal to minus 1 multiplied by tx, for x is an element of U. Then for the transformation t, linear transformation t from U to V, t plus minus tx is equal to, according to this condition, tx plus minus tx, and minus tx is equal to minus 1 multiplied by tx. Therefore, tx minus tx cancel. The tx are the element, tx is the element of the vector space V. Therefore, these are the additive inverse of each other according to the condition of the vector space, which gives a zero vector of the vector space V, and the zero vector can also be obtained from the zero operator on any element x when we apply zero function or zero linear operator on any element of U. We get a zero operator, that is minus t is the inverse, is the additive inverse of the linear operator t. Under the operator multiplication, that is for any linear transformation T and any constant C, the mapping Ct from U train to V is defined as Ctx Ct x is equal to ctx according to this condition, and if xy are any two element of U, alpha beta are the element of the field, then ct alpha x beta y, this is a result of U, is equal to c C is a constant according to this condition. T apply T, and T is a linear operator according to the definition, which is equal to this one. Multiply C to each term. After the rearrangement, alpha CTX plus beta CTY, that is CT is also a linear transformation from the vector space U to the vector space V. That is, this set is closed under the scalar, under the multi. Now our M2, the next condition is S and T are two linear transformation, and as any constant, then A multiplied by S plus T x, x is an element of U, is equal to, according to the second condition, A is a constant, A multiplied by apply S plus T on the x, S plus T x, S and T is according to the first condition, A multiplied by Sx gamma Tx, or multiply A to both term we have, that is Sx and Tx are the element of V. A Sx gamma A Tx, or rearrange A Sx gamma A Tx, As gamma A T x, that is A multiplied by st is equal to As plus At. The next condition is satisfied. Now the next condition is, for any T linear transformation T from U to V, and any two scalar A B from the field A plus B T x is equal to, according to the second condition, A plus B T x, and multiply the both term with the Tx, A Tx gamma B T x, because Tx is an element of the vector space V, therefore and AB are the element of the field, therefore we can multiply the element of the vector with the sum of the element of the field according to this condition, that is A Tx gamma B Tx. Because V is a vector space over the field F, and again according to this condition we have AT plus BTX, that is A plus BT is equal to AT plus BT. The next condition is satisfied here. The next condition is, that is T is a linear transformation and AB are any two scalar, then AB multiplied by Tx is equal to, according to this condition, AB multiplied by Tx. And Tx is an element of the vector space V, therefore according to, and AB are the scalar, then according to the definition of the vector space, we can rewrite this step as A multiplied by Btx, or A multiplied by Bt x, according to this condition, that is AB multiplied by T is equal to A multiplied by Bt. The next condition is satisfied. To check the last condition, that is if the I is the identity linear transformation and T is any transformation, apply this transformation on x, we according to this condition we have I Tx is an element of the vector space V, and I is an operator, therefore when we apply an operator on any element we get the same element, that is It is equal to T, that is the linear transformation satisfy all the condition of the vector space, that is in this case I is an identity vector of the space of the set U linear transformation UV. Therefore, we conclude that the linear transformation from V to the set consists of all the linear transformation from the vector space U to V is a vector space over the field F. And note that this field F, the vector space U and V is also a vector space on the same field F.